Hi, this is Paul from Foresight Tech. In this video, we are going to deal with the infinite series, focusing on determining convergence or divergence. Let's see the outline. First, I will introduce the basic concepts of convergence and divergence of infinite series. Next, I will introduce geometric series, harmonic series, and the test for divergence. Last, we will practice 3 questions together about how to determine convergence or divergence. Let's see the material. Here is the definition of infinite series. First, let's look at pi. And everyone knows this is one of the most famous number, right? Irrational number, pi. Okay, it's 3.1415 that goes into infinity, with infinity decimal numbers, and they cannot repeat. And we see we can write this irrational number, decimal number in this way. 3 and the 10th, we wrote 1 out of 10. And the 100th, we wrote 4 out of 10 hundredth, right? And the 1000th one, and we wrote 1 out of 1,000. And then continue, goes on. How many? Okay, infinite terms add together. So infinite terms add together, this we call series. Or you say infinite series. Okay, this we call infinite series. Okay, therefore the definition for series is this. It's just the sum of an infinite sequence. Why? So 3 is A1. The second term is A2. The third term is A3. That goes on, right? So infinite sequence and add together. The sum of an infinite sequence, we call the infinite series. And then we use summation. Or you can simplify the summation just right here. So default, which means n, the first term goes from, start from 1. Okay, not start from 0. Now, we have a serious problem. Imagine, okay, infinite terms added together probably goes up into infinity, right? So it's dangerous. Now we want a series to be meaningful. We should be defined, okay, and these added together should be not a divergence. What does that mean? Let's go into the definition. Here is the definition for the sum of a series. Okay, first we need to define a partial sum. And then we can define the sum of convergence series. What does a partial sum mean? Okay, suppose we have a series. Therefore, we have an infinite sequence, right? A1, A2, A3, that goes on. And then we define the first n terms of the sequence added together. We call it the nth partial sum of the series. This makes sense, right? So we usually use this notation. So summation I from 1 to n, and the general term is ai. Therefore, we add the first n terms together. We call the nth partial sum. Let me give you an example. Okay, so for example, you can see S1 means what? The nth, the first partial sum, which means just the first term, right? A1. Okay, what is S2? Of course, the second partial sum, which is the first 2 terms, A1 plus A2, right? The same, S3 should be the first 3 terms, A1 plus A2 plus A3. Okay, goes on. Now we have A4, S4, S5, S6, that goes on. What do we have? Now we have this. We have an infinite sequence again, right? So the sequence, if we write it in this way, S1, S2, S3. Okay, so this is a infinite sequence, and we call it the sequence of the partial sum. Then now, based on this sequence, we can define what is the sum of a convergent series. What does convergence mean? Okay, if the partial sum converges, we call it the series converge. If the partial sum diverges, we call it the series diverges. Of course, if it diverges, that series has no meaning, right? So for a convergence series is meaningful. And for a convergence meaningful series, we define the sum of that series is just the limit of the partial sum. So this makes sense, right? And imagine we learned the sequence before, right? And imagine if all these is positive terms, all the AI are positive terms, and then the partial sum will goes up. If the converges will not goes up into infinity, but we just like this kind of curve. Okay, we get a stable, and that limit we call it the sum of the series. Okay, and now let me introduce a very famous convergent series. Here is the series. We call it geometric series. And suppose we have a sequence. The first term is a. The second term a times r. The third term a times r squared. And then a times r the third power. Can you see why I call it geometric? Because now the power goes up and up. Okay, so we added these series together, a sequence together. We call this geometric series. And we have this. Okay, we have a name. Let me show the first term. See, a, this is the first term, right? And another parameter, which is r. Okay, r we call the common ratio. Okay, so let me put here. And r, a is the first term, right? So a is just the first term. And r, we call the common ratio. Y is a common ratio. And imagine, see, the ratio between the second term and the first term is r. The ratio between the third term and the second term is r2. So we call the r is a common ratio. Okay. Therefore, the series is like the sequence like this. Start from the first term a, and then times the common ratio. We have the second term. From the second term times the common ratio. We have the third term, and then times the common ratio. Common ratio goes on. Okay, and let's look at the notation. Okay, this is geometric series. We use summation is this term. The general term is a times r is to n minus 1's power. Okay, you will see why the power in the general term is n minus 1 is not n, because remember, so usually this notation we call the n, the first term, start from 1, not start from 0. So the first term, n equals 1, therefore the power is 0. That's a. Okay, so pay attention to this general notation. And now we have these results. Okay, how about this geometric series? It converges when the common ratio is between -1 and 1. All you say is the absolute value less than 1, right? And in this case, converges was the sum. The sum, we have a formula. This is important. Okay, so the sum just equals a over 1 minus a over 1 minus r. And the last is if r is the absolute value of r greater than 1, now the series diverges. Okay, so this result is very famous, and we are going to prove a little bit later. Now let me give you an example for this geometric series. So let me draw a graph for you. Okay, so this is the example. Let me draw this. Okay, and this example is also very famous. Okay, so you're going to check. Okay, change the color. And let me put this is a square. Okay, and the side is 1. So this is 1 and this is 1. Let me do this. We know what? We know the area of this square is 1, right? And then we're going to break down this area into pieces in this way. Okay, we're going to cut in half and half. Can you see? Okay, let me highlight the left half. Okay, so I highlighted this part. So now imagine what is the area of the left half. Okay, of course is 1/2, right? Okay, let me write this is 1/2. And continue. Let me going to cut the right half into half again, cut in this way. Let me highlight this part. Yes, now what's the area? Okay, so we know this is a half of a half, which is a 1/4, right? Okay, do the same. Let me cut this left part into half and half. Okay, let me highlight and this right half again. Yes, now what's the area of this small half? That's a half of 1 times 4, 1/4, which is a 1/8. That makes sense, right? And then the same. Let me cut this left into 2 parts again. Okay, let me highlight and this bottom part. Okay, and then we know. So this time the area for this small part is a half of 1/8, which is 1 out of 16. Okay, you know, now if we continue, this is a little bit small, and we will do this. We'll hide this should be 1 out of how many? 1 out of 32, right? If we cut it again, see, okay, if I highlighted this part, how many? So 1 out of 64. Okay, if we continue, that's too small. I just stop. Okay, so how many? We can always continue and continue and continue, goes to infinity. And then the pieces will get smaller and smaller and smaller. Okay, whatever. Okay, imagine if we add all these area together, should be equal to what? Equal to the whole area of the square, which is 1, right? Let me write down. That's a sequence, okay? That's a geometric series. So let me add. So the first part is 1/2, right? And then add 1/4, and then add 1/8, and then add 1 out of 16, and continue. You know the final answer should be 1 equals the whole area of the square. See, this is very famous. We learned this probably in high school already, right? And you know this is just a geometric series. Why is it geometric series? Okay, if you like, you can write in this general way. Let me write this. If you like, you can write the sigma, summation, and each term, on the first term from 1 into infinity, and then each term is just 1/2 raised to the power of n. The first power is 1, the second is 2, the third is 3, and then 4, and then 5. Okay, so this equals 1, and this is the same, right? We say y is a geometric series. Now all we need is find the first term and find the common ratio. See, the first term a equal, the first term is 1/2, right? Yes. What's it r? If you're going to see, 1/4 is half of the first, 1/8 is half of 1/4, a 1 out of 16 is half of 1/8. Therefore, the ratio is common. That's 1/2. Okay, and then we follow this formula. See, what do we get for the sum? So the sum s should be equal to a over 1 minus r. Therefore, is a is 1/2, right? The 1 minus r is still 1/2. So 1/2 over 1/2, what do we get? We get 1. So it's the same, right? So this is the kind of verification for this formula is true. Of course, we have another notation, and one comment. If someone say this notation is different from this notation, yes, but we can change this to the general. Can we? Yeah, we can. See, if we change this, it should be like this. Because a is the first 1/2 times r is still 1/2. And then now we follow the general is 1 n minus 1. Okay, this should be the series. Do you think it is equal this? Yeah, they're exactly the same, right? If we use the power rule, the product rule, 1th power, n minus 1th power added together is nth power. Okay, so they are the same. Now, let me introduce the proof. Let's break down the proof into two parts. The first part is the karma ratio equals 1. The second part is the karma ratio does not equals 1. And when the karma ratio r equals 1, all the terms are a, right? Therefore, the partial sum equals, a plus a plus a. All the terms are a. You imagine. So, plus a. How many terms? N. Therefore, it's n times a. And now, what do we get? See? And the n times a as x as n approach infinity, this is approach infinity, right? Or negative infinity when a is a negative number. So this means what? This means diverges, right? Can you see? This means diverge. And the sequence diverge, and therefore the sum, the series is diverge, right? Now look at the second part. If r does not equal 1, okay, so let me write down the partial sum first. Therefore, we have Sn equals a the first term plus the second term a times r. The third is a times r squared. And continue, right, to the last term, which is n minus 1 y. The first 0, the power. So the last term is n minus 1. We have total n terms, okay? And then we do this. We do this symbol r times the left side of the equation. So r times the right also. If a times r, I put it to here. Okay, we line up together. A times r is here, and then times the second term, which is a times r squared, times the third term, which is a raised to the r raised to the third power, and then the second last term, which is a r raised to n minus 1's power, the last term, which is a times r raised to n's power. Okay, and we do this simple calculation. We use the first equation minus the second equation. See, what do we get? We will cancel this term, and this term, and this term even goes to here. What do you mean? It means we can cancel a lot of terms, right? And what do we get? We get Sn minus r times Sn now equals, we only have a symbol, the first term left, and the last term left. Okay, therefore we can solve for Sn. Okay, we're going to solve Sn equals how many? The right term, of course, is a. We factor a out. 1. Sorry, I get it wrong. So here is not a plus. Why? So the first equation minus the second equation. So here, be careful, this should be negative, okay? Therefore, this is 1 minus r raised to the nth power. And then over what? 1 minus r, right? The coefficient of the left. See, now we get a simple way. The partial sum is just a kind of a function. And we know the limit, right? We learned this limit before, okay? And let me write it. Keep in mind. So, because we know this limit, okay, from the last video. So we know the limit of Sn. We have 2 cases, of course. So now we have these 2 cases. The first is if r absolute value of r less than 1, which means when r belongs to -1 to 1, the open interval, right? So r raised to the nth power goes to 0. And therefore, see, we have this. We have the limit m approach infinity Sn, the limit of the partial sum this time we know, which is how many? See, The top now goes to A times 1. Okay, the bottom is 1 minus R, and this exists, right? Therefore, what? In this case, and this series, okay, which is A n, or we say is A times R raised to the n minus 1's power geometric series converge. Okay, and see, and that's the sum, right? If you put here, and we can get a S, which is the sum of the convergence series, is A over 1 minus R. Remember, that's from the formula, right? So we proved this. And the second part, of course, is R greater than or equal 1. And we put this the first together. Okay, all other cases, and is divergent, because the first case diverge equals 1 diverge does not equals 1 here. Look at it. And if absolute value of R goes greater than 1, so this goes to infinity, right? Goes to infinity. All this does not exist. Let me just write. So the second case or other cases is, and this limit, the limit of the partial sum does not exist. Let me simplify, does not exist. And based on the definition, this geometric series, in this case, okay, diverges. And that's the proof for these results. Now let me introduce another famous, is not a convergent series, but divergent series. Here is the series we call the harmonic series. Can you see the first term is 1, and then plus the second 1/2, 1/3, 1/4, goes on. And this is the sequence. Added together we call the harmonic series. And the notation we use this, right? And 1 over n is the general term. And the result for harmonic series is divergent. Harmonic series is a divergent series. What does this mean? This means add all these terms together, goes up into infinity. Okay, so let's prove. And I will introduce a proof. And in this proof, there is a trick. Okay, so let me first show you the graph. And this, I will going to draw a coordinate system. And then this y-axis. And I will going to draw this function, which is y equals 1 over x reciprocal, right? And let me draw the function probably like this. Okay. Now, and this is not a scaled. Okay. Let me put, if this is 1, this is 2, this is 3, and this is 4, and that goes on. Let me put one more. Okay. Let me put one more. Okay, so you can see it clearly. Okay, 5 is here. Okay, so let me get the function, go down a little bit more. Okay, now I will going to find something here. Okay, draw vertical line, and then I will draw rectangle. Okay, good. Let me highlight this rectangle. Now, what's the area of this rectangle? Okay, and then we know the area, this rectangle, the base is 1. The height, okay, is the left end point. Can you see is 1 over 1, which is 1, right? Therefore, the area equals the height, which is 1. Okay, do the same. Let me draw another rectangle. There's here. Okay, let me highlight this rectangle again. So, what is the area of the second rectangle? Of course, the height this time is 1/2. Therefore, the area is 1/2, right? And let's continue. I will going to draw this rectangle. Let me highlight it again. What's the area? This time is 1/3, right? Okay, continue. Let me draw one more. Let me highlight this rectangle again. And what's the area? This time 4 is 1/4. Therefore, the area is 1/4. Okay, if we continue. Okay, you imagine. Now, what do we get? And we get the harmonic series. Where is the series? And the area of all these rectangles. See, the first term 1 plus 1/2 plus 1/3 plus 1/4. Okay, all the area. Okay, the sum of the area of the rectangles. Let me write here. Now we have this the harmonic series. And let's just look at the partial sum, which is what? Which is Sn. Okay, it's good enough. Sn, which means the first n rectangle, and there's 1, the first, 1/2, the second, 1/3, the third, and continue. Goes to the nth, which is 1/n, right? And what kind of results about this? And is greater than, can you see? Okay, so greater than the area under the curve of the function y equals 1/x, right? So greater than the area under the curve of the reciprocal. And that area we know is the integral, right? The integral 1/x dx. And from what? From 1 to n. Okay, and then now we can do calculation for this integral. So let me calculate this. It's not difficult because we know the antiderivative, right? So we will use a fundamental, which means this 1/x. X is a positive number. Can you see this is the antiderivative from 1 to n? Oops, I think I get it wrong. Let me erase this. It's not 1/x. It's what? It's just x. Okay. This is the antiderivative. Now we do calculation. This equals ln at n minus ln at 1. ln at 1 is 0. Therefore, this is ln at n. You know what? And when n approaches infinity and this approaches infinity, right? So which means what? Can we look at it? Okay. And the small one goes up into infinity. This big one greater than this. Therefore, Sn also approaches infinity. Does that make sense? Let me write. Therefore, we have these results. And Sn also approach, or we say the limit of Sn is infinity. Which means what? Which means this series. Okay, the harmonic series now is diverges. Okay, so this is the proof for this result. Now, let me introduce another, we call the test for divergence. Here is the test for divergence. And we need theory 1 as a foundation. What are these theory? If a series converges, then the limit of an is 0, which means the general term should approach 0, right? And we were going to prove this a little bit later. First, let me look at this remark. Okay, the converse of this theorem is not true in general, which means if the limit equals 0 does not mean the series converge. Okay, let me give you an example. And can you see what this theory is? This is harmonics, right? And let me look at the general term. Okay, the limit is 0, approach 0. Can you see? Do you think the series converge? Of course not, right? And the harmonic series diverges, of course. Therefore, the converse is not true. Now, how to prove this theorem? Okay, so we need a little bit of trick. Let me show you here. All we need is this, the general term. Let's look at the general term, an. and we can write the an in this way: a Sn minus Sn minus 1. What does this mean? Okay, and Sn is the first n terms added together. Sn minus 1 is the first n minus 1 terms added together. Of course, subtract is an. Okay, that's what we need. Here is the trick. Let me highlight. Okay, if we have this now, we know. Okay, because the series converge, which means Sn approach to a number, right? Which means this is the limit exists, and if say the limit is s, see, and this will approach s, right? The first term approach s, the second term also approach s, right? And therefore s minus s is 0. Is this a proof? Yeah, definitely. Which tell us the general term approach 0. Okay, so we have theory 1 as a foundation. Now we have a important result. We call the test for divergence. Okay, and what kind of series should be divergent? And is this: if the general term does not approach 0 or does not exist, which means what? Which means the opposite of the limit equals 0. See, if it exists but not equals 0, or does not exist, and this is the opposite, okay, as this condition. And then this kind of series should be divergent. Why? Imagine. Okay, so all we need is the theory 1. Okay, so can you see? Let me put here. This is true, definitely. All we need is by the theorem 1. We just proved. We can argue this result by contradiction. Okay, if this condition exists, and then if this series does not diverge, which means converge. See, if this converge, look at this theorem. And then we should get what? We should get the general term equals 0. However, the general term does not equal 0, right? Which means contradict. That means the series should be divergent. Okay, so now let's practice a few questions together. Here is the first question. We need to determine the convergence or divergence for these two series. And look at the first series. This is a geometric series. Why I say this? We can compare, and to our geometric series, the formula. So what do? We have to manipulate it, We're going to manipulate. We change the form to this formula. How to? It's not difficult. All we need is do this. 5 up here, and then we change 1 over pi parentheses raised to the nth power. Now almost, right? And the only difference now the power. So in our formula is n minus 1. Here is n, but we can manipulate it, right? So we can take 1 down. Therefore, equal this. So 5 times 1 over pi, which is 5 over pi. And then times 1 over pi. Now we only have n minus 1's power. See, that's exactly geometric series, right? So what is A? A is 5 over pi. What is R? R is 1 over pi, right? So what do we know? We know this is exactly geometric series now. So that's geometric series. So very good, we learned. And also we know A does not matter, but R is important. So this time R is 1 over pi. Pi is 3 point something, so this is a decimal. Point something belongs to -1 to 1, which means the absolute value less than 1, right? What's the result? We can get converges, right? So this series converges. And look at the second. It's very similar. Look at this complicated, but we can manipulate it. Okay, with dr fit this geometric series. Let me show how to manipulate it. So I will going to manipulate it again. See, and we can do this. So this is a sigma. What I will going to do, I will going to break it down. These 2 raised to this exponent. I'll break it down into 2 parts. I will take a -1, this power down. So what do we have? We will have this kind. The bottoms, they are 3n. The top is 6 times. So 2 raised to the 2's power. And then we have n. And then times 2 raised to the -1's power. Can you see? That's we just break it down, right? Now, let's focus this part and this part. Why? Because they have the same power. Okay, so we can put them together. Okay, if we put them together, see, what do we have now? Of course, 6 times 1/2, right? Which is 3. So we have the first constant number is 3. Now we have what? 4. 2 raised to the second power. 2 squared is 4. So over 3. And then raised to the nth power. What do we get? Geometric series, right? A is 3. And what? R is 4 over 3. But you say the power is different. Yes. Okay, we also can modify a little if you like. Okay, we're going to modify a little, so we have exactly this. We take this one down. Therefore, 3, the constant goes to 3 times 4 over 3, which is 4. Right? And then times what? 4 over 3 raised to the power of n minus 1. This time they are exactly the same. Okay, so A is 4, R is 4 over 3. That's what? Geometric series. Let me simplify. This is geometric series, right? And also we know this time was R. So R is 4 over 3. So 1.333. Okay, this is what? This not belongs to -1 to 1, which means the absolute value greater than 1. So this time was the result. Definitely we get this one is diverges because the results give us. Okay, now let's go to another question. Here is the second question. We have a series. Do you think this is a geometric series? Okay, so I say no. Why? Because the ratio, imagine, this ratio is not common. Okay, we do not have a common ratio. And they see the first ratio is 1/2, but the second is not 1/2. The third is also not 1/2. Okay, so how to do? But you know we have another. So we got harmonic, right? And you see this is exactly a harmonic series. And because we can just change, okay, manipulate. What to do? I just factor out the 1/3. See, what do we have? 1 left, 1/2 left, 1/3 left, 1/4 left. Okay, so continue 1/5, 1/6, like that. What do we have now? And this term is what? This is a harmonic, right? This is a harmonic series. Harmonic series is diverges, right? So divergence times constant number, of course, diverges, goes up into infinity. So this is a diverges. We have the results. Now, let's see, practice one more question. Here is the last question. And we see we have this series. Okay, this time is super easy. Okay, why? Because if we look at the general term, and it will not approach 0. Imagine. Okay, so let me going to see. Look at this general term, which is 1/4 plus 2 over 3 raised to the nth power. Okay, because we have a result 2 over 3 raised to the nth power approaches 0, right? Therefore, the limit of this is 1 over 4 plus 0 is 1/4. Does not equal 0. Do you remember we have a result? We call the test for divergence. Therefore, by test for divergence, this series is diverges. Okay, and by test for divergence. Okay, so that's all. Thank you. I hope you enjoy learning on this topic. If you have any question, please leave your comment. If you like this video, please give me a thumbs up. Thank you for your support. Please don't forget, you are very welcome to subscribe to my channel for more videos. In the next video, let's see, we will deal with the sum of a convergent series. Hope to see you there. Thank you. Have a nice day. Bye.